Welcome to the introduction of MEMS. We are going to talk about reducing waste and discuss MEMS high volume production, yield, and quality control. My name is Chang Liu. As you can imagine, since the functions of integrated circuits are very critical, their quality has to be very strictly controlled. If you have a bad circuit that doesn't work, then it does nobody any good. So we are in the series of foundations of MEMS. We talked about overviews, discussed fabrication process, then we talked about mechanics and MEMS transducers. The quality control is very important, especially challenging when the size of the circuits are shrinking and the number of circuits elements are increasing. Because let's say if you have a billion transistors on a die, if a single transistor doesn't work, then you can argue that the entire circuit doesn't work. If a single gate contact at a MOS transistor doesn't work, then you can argue that the entire 1 billion transistor doesn't really work. So how do you identify the presence of a single defect out of a billion? And that's the challenge, right? And how do you do that extremely fast? And so it doesn't waste too much time and doesn't waste too much chip real estate. A lot of these foundries are dedicated production units. And foundries are different from designers. In the past, a designer makes a chip design and their company actually makes it. And nowadays, the design community and the foundries are very much separate. Foundries focus on production. The purpose of a foundry is to develop process suitable for volume production for 1 million wafers a, uh, a month, for example, to prove the feasibility and to conduct small volume production. Some of the foundries are more for ramp ups, and some of the foundries are more for massive volume production. The key measures of a foundry process development include process yield, that's how many dies out of a wafer work, cycle time, that's how long does it take from the start to finish the process of uh, of an entire wafer production. The facility utilization rate is very crucial because if your foundry customer sees that you have no room left for your facility utilization, they may not like it because what if their volume increases and you cannot satisfy their scaling demand? The gross margin and net profits are important because if you operate a foundry and it really doesn't make money, then likely your stock price would be very low. Then likely the morale of your company's employee would be low. So you will be losing good people. And foundries really require good people. One of the key concepts of quality production is that out of about a million uh, transistors out of a million dies, uh, the allowable defect is about three. So 3 out of a million is typically what's defined as 3 sigma on a normal distribution chart where the errors are outliers. Uh, Only when you have a 6 sigma, you have a allowable 3 out of a million, right? Now think about it. If Apple makes 3 million cell phones, if Apple makes 1 million cell phones and three of them don't work and they ship it to the customer, what do you think the customer would say, right? They're going to complain it online. And if three um, battery control chips on a portable power bank doesn't work, then what's going to happen? So actually, three out of a million is a very strict requirement, and any kind of production unit must be able to satisfy this. That means they must be able to control the tightness of their air distribution, and this is a big challenge. One of the very big challenges nowadays as we get into the post-Moore's regime and where the chips are having gates that are smaller than, say, uh, 5 nanometers node, is that the testing of their functionality becomes very important. Ideally, you want to test the wafers before they are packaged because packaging takes time and packaging takes money. You don't want to waste time packaging a bad die. So chip probing refers to the art of probing the functionality of a die while they are still on a wafer. And this requires uh, large arrays of contact pads that can touch down with all the uh, dies on a wafer at the same time and provide various kinds of electrical tests. And this is a very big challenge because the testing itself takes time. Uh, a company that I work for, Form Factor, they make springs. The springs are for testing high bandwidth memories. Those springs are actually made by using MEMS technology. You can see the uh, tips made by molding electroplating of a cavity and cantilever beams and so on. So obviously, due to the limitation of time, we don't have a lot of time to discuss this topic, but this is actually very interesting and very exciting technically. Thank you.